Hello, everyone. Welcome. How's it going? Great. Hope you all had a nice weekend. Good to see you, sort of, out there. So the plan for today is to wrap up the discussion with continuous random variables. So last time we talked kind of really generally about them. What does the PDF measure? What does the CDF measure? How do we move between the two of them? How do we calculate probabilities by calculating areas? All of that stuff. So today, just want to make sure that there aren't any questions remaining about that material, and then we'll kind of jump in and take a look at a couple of particularly useful continuous distributions. Mainly the normal distribution is going to be the most important distribution for us. So we'll take a look at a couple of commonly used continuous distributions. But before we get started, are there any general questions about things? Okay. Okay, so the video for the reading quiz and then the questions that you had, this is basically what the video was on. And so just to kind of quickly recap last time, so if we have a PDF, right, we denote that with the lowercase f. And we want to be careful about how we use these functions to read probabilities, since probabilities, how likely it is that the random variable takes on certain values is going to be equivalent to an area underneath this graph. The cumulative distribution, right, so that tells us the probability that x is less than x, we can get by finding an antiderivative of the PDF. So the CDF over here is an antiderivative of the PDF. So we can find it by integrating it and coming up with a piecewise function for that. Any questions about that part of the process? And then once we have these functions, then we can answer questions like, how likely is it that x has certain values? What's the expected value, median, and variance? So if we're calculating, for example, what's the probability that x is less than 1 from the PDF, then we would want to calculate this little area, which is a triangle. So you can calculate that area of the triangle, or more generally, you can integrate the PDF over that interval of values from the minimum value up to that value. And so we would calculate the area over here. If we were using the cumulative distribution function, then we would just want to evaluate that function at that point. And this value is going to tell me what is the probability that x is less than that. Questions about that? So generally speaking, if you have the CDF and I want to calculate this, it's much easier to use the CDF because we just evaluate it at that point. We've already done the integration over there. Expected value, right? We would integrate x times the PDF, and so that's what's inside here. Here's x, here's the formula for the PDF. That tells us the mean or the expected value. To calculate the median, one way that we can do it is set the CDF equal to 1/2. And what we're trying to do is find the value of the random variable so that the probability that x is less than that value is 1/2. So that's why we set it equal to 1/2, find the corresponding x value, which in this case is square root of 8. And what's significant about that median value is that it splits the area in this graph into 2 equal halves. And then kind of the last thing, this was actually not on your quiz, but if you wanted to calculate the variance of this random variable, then we can use the shortcut that says we can calculate the expected value of x squared and then subtract the expected value of x squared. So this part over here is this integral, right? To calculate the expected value of x squared, we would integrate x squared times the PDF. And then over here is the expected value of x, which was the square root of 8 squared. So this has a variance of 8, and therefore the standard deviation would be the square root of the variance. So we actually get, in this case, the standard deviation happens to also be square root of 8. That's just a coincidence. It's not the case that standard deviation is always going to be the same as the, say, like the median, which happened in this case. So that was a quick run through of the video and the quiz. Results of the quiz look pretty good. Are there any questions about these examples? So you have some homework questions similar to this that'll be due for next week. So that assignment is up. Actually, don't forget tonight you've got homework 2 due tonight. Homework 3 will be next Wednesday, next Monday, excuse me. Okay, so if there aren't any other questions, please feel free to stop me along the way. Then I want to move on and talk about the rest of the chapter 3, at least the material that we're going to cover with continuous random variables. So this is worksheet 4B, which is posted up on Canvas. And so before we kind of move on to the normal distribution, the uniform distribution is a distribution where every outcome is equally likely. So when we have uniform distributions, the PDF is going to be a constant value, since every value x has the same likelihood of occurring. So that's where we get a straight horizontal line like this for the PDF. And so its formula would just equal that constant we find by taking 1 over the difference of the maximum value of x minus the minimum value of x. And that's what B is representing, the maximum value, A, the minimum value. And so this is just to kind of use the same sort of approach that on the reading quiz. If we wanted to find an antiderivative, if we wanted to find the CDF, then we would calculate the antiderivative by integrating the PDF. And this gives us a linear function. So it looks like that. So it's going to kind of increase at an equal rate from its minimum value up to its maximum value, sorry. And then it's going to just flatten out at 1. And then we have some shortcuts. So these are all kind of general formulas. You're welcome to use these shortcuts. And then we've got shortcuts for the expected value and the variance and the median. And if you're curious where those formulas come from, it just comes from doing the same thing, calculating the general expected value. You just have nice shortcuts in this example. So this is a particularly nice distribution to work with, but most things don't have all equally likely outcomes. Yep, Max.
Those shortcuts, are those only for uniform distribution, right?
Yeah. Yes. Yeah. So in general, which was the stuff that you had to do on the reading quiz, that wouldn't work. Yeah. So yeah, then you're kind of stuck doing things the long way when this is something more complicated than just a constant. Yeah. Was there anything else? Okay, so that's about as much as I want to say about the uniform distribution. I want to kind of focus most of the time today talking about normal distributions, since when we start doing statistical inference and we start sampling things randomly over and over and over again, we're going to see that the underlying distribution for these sample spaces is actually going to be normal. So definitely, most common distribution, certainly in a statistics class. And so normal distributions, we are given by two parameters. So if you remember back to the discrete random variables, we had certain random variables and their distributions were determined by things like n and p. And if we could identify what n and p were, then we could do a whole bunch of calculations. For normal distributions, the two parameters that we need are the mean and the standard deviation. So these are not things that you need to calculate. These are things typically that are provided to you that describe the distribution. And so we would say something is normally distributed by saying X follows a normal distribution. First comes the mean, then comes the standard deviation. So we use the Greek letter mu for mean. And we use a lowercase sigma for standard deviation. So we kind of take the Greek equivalents of the first letter of each of those. So the mean tells us where the distribution is going to be centered, and the standard deviation tells us how spread out the values are, how wide the distribution is. And in this case, since the normal distributions are symmetric, right, meaning the left side looks exactly the same as the right side, we don't have a formula here for the median. The median and the mean are equal in this case. That only happens for symmetric distributions, let me just say. Generally speaking, they're not the same thing. They're measuring something a little bit different. So we typically don't refer to the median when we're talking about normal distributions. We use the mean as a gauge for the center. So the larger that sigma gets, what's trying to go on in these pictures, right? If we have larger standard deviation, it doesn't have more area. The area beneath all of these curves is 1. We just kind of smush, the peak goes down and it gets a little bit wider. Whereas the mean just kind of would be like a vertical shift of the graph. Yeah, so over here, things like heights are typically normally distributed. You can see here's a height. This was not my graduating class. It was a bit before me. We actually had color photographs when I was an undergrad. So, but this is an old picture of a bunch of students. I think this is at UConn who lined up in height. And the people wearing white are the women and the people wearing black are the men. And so you can actually see kind of just if you looked at the men themselves, they would also follow a somewhat normal distribution for height. Okay, so we need to figure out how we're going to calculate probabilities from normal distributions. And we'll see that the actual formula for the PDF is a nightmare. It involves e, n, pi. It's one of the few functions that involves like 2 different irrational numbers. And we're definitely not going to want to integrate things following normal distribution. So we'll talk about how we can use R, but first I want to talk about what's called the empirical rule. And actually, I think this is like the most intuitive way to think about normal distribution. So if you get a good grasp of how this empirical rule works when we start to construct 95% confidence intervals to estimate things, it's not going to be surprising. Hopefully it shouldn't be surprising how we construct 95% confidence intervals if we're kind of thinking back to this rule. So normal distributions, they're bell-shaped. And if you're kind of thinking about what situations would follow normal distributions, these would be situations where the most common value is the mean. And then as you move away from the mean, in either direction, it gets less and less likely. So in other words, like heights tend to be normally distributed. Most people are about average height, but you're equally likely to be taller as you would be shorter, and that's why we follow this normal distribution. So what the empirical rule is telling us is that if we're at the mean over here, and we go one standard deviation above and below the mean, then 68% of the data should be between one standard deviation above and below the mean. Going 2 standard deviations out is going to give us 95% of the data underneath the standard distribution, normal distribution. And then if we go as far as 3 standard deviations out, that's going to incorporate just about all of the data in the population. So about 99.7%. Okay. So let's kind of take a look at an example to see how we can use this empirical rule to calculate things. And I just want to be clear that when you're doing some of your homework problems or when you're working on the exam, there will be some questions that are going to ask you to use the empirical value to estimate this. So don't just think like we've got technology, so I don't need to do anything by hand. It is important to kind of think about this because a lot of times you might not be sitting in front of a computer when you're trying to answer some of these questions. So one application of this is, so I work in public policy. When I'm not here, I work in Kennedy School of Government at Harvard. And so we do some data analysis for public policy, military, lots of governments from around the world. And so we got approached by Israel a long time ago, and they were trying to create some policy that was going to combat kind of body image issues. So they wanted to prevent having models that are unhealthily thin, that are portraying an unhealthy kind of body type. So they asked us to kind of come up with what do you think would be a reasonable cutoff for that. So we use a metric of body mass index, since you don't want to use weight because people are different heights and that might affect things. So body mass index is a measurement that incorporates both your height and your weight. And so these are things that tend to be normally distributed because most people are about average weight, and then you're equally likely to be a little bit over the average as you would be below the average. And so let's let random variable x be a random male in Israel who's picked out, and that's going to be their body mass index. And so based on some data, we came up with a model for the distributions of body mass index for men and women. The mean body mass index is about the same for men and women, a little bit bigger for women. The spread is also about the same. It's a little bit bigger for women. So here's a good process for doing these. So you're going to have some questions that are going to ask you to like sketch a graph, illustrate what this, what area corresponds to this value, and then use the empirical rule to estimate that proportion. So when we're doing this, sketch bell curve. That's about as good as my bell curve gets. And then we're just going to mark off our mean and our various standard deviations. So right in the middle, since we're looking at the men, we're working with this normal distribution. So I'm going to mark the mean. Then we're going to go 3 tick marks above, 3 tick marks below. And again, this is more of a like a back of the envelope calculation. So we're just, we're not drawing at least I'm not drawing a perfect normal distribution, but you want your tick marks to more or less be like equally spaced out. And each tick mark is going to be another increment of the standard deviation. So here the standard deviation is 4. So I'm going to go up by 4 each time. And I'm going to go down by 4 each time over there. Okay, and then we're going to shade in this area. In this case, it's asking us for the area between 26 and 30. So over here, we can say that the probability that X right, that would be that shaded area underneath the normal distribution between 26 and 30. Any questions so far? Okay, so now if we're using the empirical rule, anybody want to, you're welcome to chat or say it in, what would the empirical rule tell us that this area should be approximately equal to?
(34% of the data?
Yeah, thank you. Julie, do you mind sharing how you got that?
Yeah, so I got that because I know that we're in the light pink area, which is 68%,
Yep.
but it doesn't go past the mean, so you have to cut it by half.
That's right. So we can use the symmetry property here. So there's a couple of really kind of useful things here to note. And one is that this is symmetric. So that means if this is 68% of the data, and we divide that region in half, half of it should be to the right and an equal amount should be to the left. So that's where here, I'm just gonna express these. When they ask you for proportions, then typically that means leave it as a decimal. Yeah, so that's 0.34, 34%. So yeah, that's telling us 34% of men in Israel have a BMI between 26 and 30. And another useful fact about this distribution is that it's almost like we have all of these different puzzle pieces. And if we add up all of these areas, all of the areas should add up to 100% of the data. Any questions about where the 0.34 came from? Okay, so if we were to do a similar thing, but now we're thinking about women and we have a different range of values and we want to calculate what proportion are in here. Now we just want to make sure that we adjust where we place the middle. And now each of these tick marks should be equivalent to 4.5 body mass index. So going up to the next tick mark puts us at 31, 35.5 and 40, 22, 17.5 and 13. So I do think it's a really good habit to get into sketching pictures of this. I'm a very visual person. It helps me a lot, and it's going to help us even more as we're moving forward. So now we want to calculate this area over here. From 22 up to 35.5. And so that's this area that we've shaded. Anybody want to chat or talk, share your answer for this one?
I think it's 0.915.
How did you get that?
So it uses all of the whole area for where it would cover 68%, and then it also goes one more over, so it would be half of, or okay, so the difference between 68 and 95 was, let's see, what, 27? And so you just cut that in half and add that to 68.
Okay, so let me make sure I'm getting this right. So my picture clearly is not drawn to scale, but that's right. If we kind of go, whoops, this is what I want. If we go in here, that should be symmetric. That's one standard deviation above and below. So that's the 0.68. I think you had the right idea, Stephanie. I think maybe just the calculation was off a little bit. Yeah.
Would it just be the 95% divided by 2 since it's within 2?
So yeah, the question is, how do we figure out what this area is over here? There are different ways of doing it. And so if I was understanding Stephanie correctly, she was saying, well, if we subtract 0.95 from 0.68, that should be the area that's between those two. So I'll just shade that in some other color. Right, so that area right there should be the 0.95 minus the 0.68. But we don't want both of those things. Again, sorry, my graph is not to scale. Those should be approximately equal to each other in green. And since we only want one of those pieces, we can then divide that by 2. And this gives us when we divide by 2, just that little area in between. That didn't come out very nice. And I think when we add those together, yeah, it comes out to, I think you had an extra maybe 10% there, yeah. Anybody think about it differently? Okay. And I won't, there are probably other ways that you could divide this up. It might be easier. It's a subjective thing, but there are different ways. Basically, you're just trying to add up the areas of different pieces. So there's just different ways that you could slice it. Okay. So any other questions about that? Okay, so here's a useful thing to think about. So oftentimes we might want to compare values from different distributions that have a different mean and a different standard deviation. So it might be nice to have a kind of more neutral measurement for how extreme values are in our distribution. So we could ask a question like, well, how many standard deviations from the mean, which is for males, that was 26. So if a male has a BMI of 21, how many standard deviations is that from the mean? And so it doesn't fall perfectly on one of those ticks, right? It would fall someplace over here. And so just kind of informally looking at the picture, we can see that 22 is 1 standard deviation below, 18 is 2 standard deviations below. So it should be somewhere between Do you guys pick up that sound? There's like a drag race on my street, apparently. Okay, so yeah, so somewhere between 1 and 2 standard deviations below the mean. Okay, and it's useful. This is really important to indicate not just how far is it from the mean, but in what direction. If we want to be more precise, then what we could do is calculate the distance. So this tells us that 21 is 5 BMI points below the mean of 26. but this is not saying like how many units of BMI is that below the mean. It's saying how many standard deviations is it. So what do you think would be a good operation to do here to try and describe this distance, not in terms of units of BMI, but in terms of units of standard deviation?
You can say like how many, or yeah, how many standard deviations like each BMI point is worth. So like since 4 BMIs is 1 standard deviation, then 1 BMI would be like 0.25.
Yep. We're just going to divide that by the standard deviation. So that kind of cancels the units out, right? The standard deviation also has units of BMI. So this is 5 BMI below the mean. Each standard deviation is 4 BMI. So taking the ratio there, that's exactly right, thank you, would give us minus 1.25. And now we don't have any units here, right? This is minus 1.25 standard deviations below the mean.
As long as you put like the negative, do you always have to specify
Yeah,
what?
thank you. Yeah, you're right. That is implied with the negative. Thank you. So that might be a better way of avoiding like a double negative. Yeah. So yes, that's really important here in that this fact that it's below is incorporated with that negative sign. Okay, then kind of describing this distance of this value from the mean in terms of standard deviations is going to give us a more general way of working with probabilities and normal distributions. Any questions about that? Yeah, and so that calculation is exactly what we call the z-score of that value. So if you've heard of z-scores in a previous statistics class, this is what you were calculating if you didn't realize it. The z-score is calculating, it's describing how far my value is x from the mean in terms of standard deviations. And so what we can kind of see here is that once you go beyond 3 standard deviations above or below the mean, there's pretty much very, very sparse data at that point. So so this gives us a way of thinking about like what range of values seem probable for a random variable, which values seem very unlikely to occur. So when we standardize things, it just gives us a way of relabeling the axis of the x-axis here, the horizontal axis. So over here, we were describing things in terms of BMI, whereas over here, we're describing each of those values in terms of what their z-score is. And so this standard normal distribution has a mean of 0 and a standard deviation of 1. So it's centered at 0, and each tick mark corresponds to 1 standard deviation. Any questions? Okay, so yeah, this empirical rule that we started with is great. It gives us like an informal way of estimating probabilities for a standard normal distribution, but like it only works nicely if we're at like perfectly one of those cutoffs, which we almost never are. So if we wanted to calculate something like this, like how extreme is 18.5? Like what percent of women in Israel did we just rule out? Did we just ruin their modeling career just because they were deemed too thin? So in this case, the BMI for women we denoted with a y. So we want to calculate what is the probability that y is less than 18.5. Okay, sorry. Yeah, so that's eventually what we're trying to do down here. And the idea is, well, let's think about how far this point is from the mean, and that'll give us some sense of how much area is beyond that point. So we can calculate the z-score here by taking x, in this case, we'll call that a y value, minus the mean, and then dividing that by the standard deviation. So in this case, we're thinking about, well, how far is BMI of 18 from the mean, which for women was 26.5. And then let's convert that distance of BMI units into how many standard deviations that would be. And so I believe this comes out to minus 1.7777. Well, the 7 repeats. Any questions? Does anyone want to just say or type what does this number tell us then?
How far away it is in terms of standard deviation?
Yeah, so this is telling us that like a woman in Israel, I'll preface that it differs regionally, but a woman with 18.5 BMI so that's telling us how far away they are. And in this case, that would put it really kind of closer to there, right? In that one, because it's a little bit closer to -2 than it is to -1. And if we want to kind of just get an informal estimate for this area, how much area is to the left of 2 standard deviations below?
$17.5.
So how much area would be between the 2 and -2 standard deviations?
95%.
95.
Yeah, so 95% is in here. So in other words, how much area is not in the middle? So 95% is in the middle. What's outside?
0.05.
Yeah, so we're missing 5%. And we only want the half of that missing piece, which is on the lower tail. So we would say over here, this area over here would be half of that 5%, right? So this area over here is about 0.25. And then I could similarly think about getting an upper estimate for that, because I know that the area is going to be somewhere between how much area is to the left of -2 and how much area is to the left of -1. So for this one, we could say in this area, it would be the stuff outside of the middle 68% that we then would divide by 2. So that is 16%. Yeah. So using the empirical rule, we can get some sense of what we expect. Clearly, that's a big difference, so that's a big range of values. But we can see that it's probably a bit closer to this, since it's a little bit closer to the -2 than it is to the -1. So before we kind of use some technology for these, any questions about z-scores or how we've been using this empirical rule to estimate probabilities? Yeah, and I really encourage you to be drawing pictures, if not on your homework, at least on the side. I think that will really help you a lot moving forward. So if it's an adjustment to do that, I think it's worth kind of putting some time into kind of connecting this to a picture will help a lot. Okay, and so the PDF for this formula, which is called the Gaussian, so this was developed by Gauss, one of the greatest mathematicians, and it's this horrible looking formula. So it involves the square root of pi, it involves e, and it depends on these two parameters, the mean and the standard deviation. So if we actually wanted to calculate this with the assumption that like the smallest BMI that you could have is 0, then we'd really need to integrate something like this. And I promise you that not a single person here or elsewhere in the world can evaluate this analytically by finding an antiderivative and going about it that way. The best that you can do is use Riemann sums to approximate this. Yeah, there's a question.
Well, I was just curious with the square root of pi, how that would be theorized, I guess, since it's a continuous number, how we would think about that.
So yeah, so the x is a random variable. So this PDF is just is the formula that gives us this curve right here. So if we wanted to actually plot this, then what we would need to do is graph this. And so in this case, this was the male BMI. So this formula would have like a 4 there. It would have 26 over here. It would have a 4 over there. And the only variable here is x. So we would ideally want to like input an x value and see what the output is. In practicality, I don't think we'll ever see this formula again, since we've got nice technology that's going to help us calculate these. But I do think it's nice, maybe not nice, to just kind of see that how crazy this formula is, just to model something maybe that we all are somewhat familiar with, looking at these bell-shaped curves. But there is a formula for it. However, that formula doesn't help us with the calculations necessarily because we can't integrate this. So what we do, or what a computer does, it does this sort of thing, you know, the Riemann sum sort of thing. But computers can, you know, take the limit as the width goes to 0, and it can get a very good approximation for it. So one way to do this is with using standard normal distribution. That's kind of like the old school way. That's probably the way that these people were doing it back over here. They had this nice standard normal distribution table. These are useful actually, because again, you're not always in front of a computer. So I'll just kind of explain how to read that table if you want to do it that way, or you can use R. So I'll just say You don't have to use the table. You don't. You probably will have to use R. So I'll kind of recommend that you might want to use R and not the standard normal distribution table. But if you've seen these tables before and you're curious how they work, what we wanted to do was calculate the probability that a woman in Israel has a BMI which is less than 18.5. So this is equivalent to saying, what is the probability that we would pick a value that has a z-score which is less than minus 1.78. So we can standardize the normal distribution, and then these are up online in case you would like to download them on these normal distributions. Then what I do is I want to work with this z-score of minus 1.78. So I come down the z column until I get my first decimal place of accuracy. And then, so that tells me what row to look in, and then to pick out which column, I would pick the second decimal place. And then that entry in the row corresponding to the first decimal and the column corresponding to the second decimal tells us exactly what the area is, or at least in this case, gives us really a more accurate estimate for that. And again, to get in the habit of kind of illustrating what these things look like, that's telling me the area in that tail to the left of 18.5. So actually, it's really quick to use the table. That's kind of the nice part about it. So I would say, if you're not in front of a computer, these are actually really handy to use. If you're in front of a computer, then that's what you should use. Okay, and so the formulas for R are pretty similar to what we had with, binom and the Poisson distribution and so on. When we're reading continuous distributions, remember, we're always looking at areas. So we would never want to use a d-norm. Since d-norm would tell us like the y-coordinate of that point. It would tell us the height of that point, which really doesn't tell us anything about probabilities. So make sure that when you're working with these normal distributions, you're always using the p-norm there. So p-norm calculates the probability that the random variable x is less than an indicated value. So p-norm tells us area to the left. And sometimes you want to get the area to the right, or you want area in the middle, but we can take advantage of just this one p-norm function to calculate any area underneath the normal distribution. So the input would go x, then the mean, then the standard deviation, or if you've already standardized things, you could choose to do it that way. They'll give you consistent answers. So just to kind of hop over into R. Then over in R, we would, for example, go p-norm 18.5, 26.5 was the mean, 4.5 was the standard deviation, and we get something that was pretty close to what the table told us. If I use the standard normal distribution, we would get a pretty similar thing. Keep in mind, this one up here is probably more accurate because down here, I rounded that off a little bit. So the question is that Yua asked is, can we use tables but not R during the exam? Under normal conditions, non-pandemic conditions, and we're all sitting in the same room, I wouldn't expect everyone to have a computer, and so I don't allow R during the exams. Since we're here in this pandemic world, and by definition, you're going to have to be in front of a computer when we're taking the exam, you will be allowed to use R during the exam. However, on the exam, I'm going to ask you to enter what was the code that you entered into R. So you're welcome to use R as long as you show supporting work, and that supporting work would just be, here's what I entered into R, this was the output. So I could literally just copy and paste this into a Word doc, and that's sufficient work. Okay, so I want to give you guys a chance to practice some of this, or at least to practice an example here. So I'm gonna break us up into rooms in a second. Let me get my screen back. And I'd like us to just work on question 7 in some breakout rooms to make sure. Sometimes you don't know if you have questions until you're just thrown out to try this on your own. So the idea here is we're looking at now a distribution. Oh yeah, so by the way, for women, that's right. So this, that was about 4% of Israel's population that we suspected would have a BMI that was less than that cutoff point. So that's a pretty extreme BMI. Yeah. Okay, so in this example, we're looking at distribution of IQ score. And so 100 is the mean IQ, and standard deviation of IQ is 16 points. So when you're going through these, you know, it might help to just sketch a picture here, just so that when you do your calculations in R, you want to make sure that they make sense, right? Sometimes you might enter something in R and get a number that's really small when you can see that the area should be big. So these are good ways of kind of checking your work in R. But so here's the distribution. These are some slightly different problems. We didn't necessarily talk about these yet together. So I'm going to just be curious to see how you guys do with extending some of the ideas we've talked about to answer some different problems over here. Any questions before I set up the breakout rooms? Okay, so the rooms are open, and you and I will kind of cycle through, see if you have any questions. Yeah, so in part A, I think at least I was able to go through those with the groups I was with. So the area would look something like this, and various ways of thinking about it, but one way is to think about the fact that inside of here is 0.68, since this is one standard deviation. So then we can track down this by saying, well, it's all of the area minus that 0.68, but we don't want this tail as well on the left. We only want this one. So that comes out to 16%. You certainly could have used formulas as well, not with that in there. But keep in mind, this would tell us the area to the left. And so if we want the area to the right, we would need to just correct for it like that. And so R should give you something, if not the same, very, very close to that. Any questions about that one? Okay, then in B, right, we would take this same formula, except now the unknown is the value x. We're trying to find out what that is. So in this case, we've got unknown x. That's what they're telling us to find. We know that the mean is 100, and we know that the standard deviation is 16. So this is just an algebra problem, right? Solve for x. So we would multiply both sides by the 16 and then add the 100. And this tells us that Marilyn Vos-Savant had an IQ score of 186.4. That's off the charts, obviously. We saw that there's almost nothing beyond 3. She's in like a whole class by herself over there. Any questions about that? So it's just kind of inverting the process that we used to find z-scores before. Okay. In C, I don't know how far groups got. I suspect maybe not all the way over to here. This is asking us to calculate, here's the mean, which is 100. So area-wise, it's asking us to calculate this. And this 75, right, falls somewhere over here. So it's not a perfect tick mark of a standard deviation. So we can't really use the empirical rule to get too accurate here. Did any of the groups get to this part?
We're trying to work through the R command for it.
Yeah. So what did you enter in R?
Well, we knew that the qnorm would be 75, 116. But I think we're just still working through, you know, if you subtract that from a half, I think was what one of my group mates said.
Yeah, that would work. So this area over here, just to identify what it is, right? That would correspond to this area right here. So this gives us area to the left. Which, although is not exactly what this is asking us to do, that's really useful to know if we want to find that. That's right. So we could use the fact that, well, 100, that's significant because it's the mean. So over here should be 1/2 of the area, and over here is 1/2 of the area. So if I know what the stuff in orange is, and I know that the total area to the left of 100 is 0.5, then if I subtract that from 0.5, it's going to tell me the area in between 100 and 75, which comes out to about 44%. Any questions?
Is R kind of the best way then that you would calculate that?
I think so. Yeah. Yeah, R or the table. I think the more comfortable you start getting with R now, the better. So I would definitely encourage you. It's not cheating if you're using technology. We're going to be using R a lot. So I definitely would encourage you to do it multiple ways. You know, if you want to use the empirical rule and then check, make sure that R is telling you the same thing. Yeah. Okay, so lastly is we want to find the 90th percentile. So what this is saying, what is the IQ score so that the probability of getting that score or less is equal to 0.9. So I'll just call this value x. What we're trying to identify is the value of x that gives us an area of 0.9 to the left of it. So we actually want to do like the inverse process of what we've been doing. So we've been inputting a value for X. We've been figuring out the area. Here we want to kind of invert that process. And so there is a built-in function in R called qnorm. The Q standing for quantile. So this is like essentially the inverse of the pnorm function. And so this function takes in 3 inputs. Instead of inputting X into the first position, we input the area that is to the left. So in this case, we would say qnorm 0.9, 116, and that comes out to 120.5. So one additional sort of distribution function that we haven't used yet is when we put the quantifier Q in front of that norm function. So the 2 really useful functions when we're working with normal distributions are pnorm and qnorm. And again, this one says, given an X, find the area to the left. Whereas this one says, given an area to the left, tell me what the X value is that cut off that area. Okay, so sorry, we'll stop here. For next time, we're going to start talking about chapter 4, which is going to deal with joint distribution. So when we have a situation that depends on more than one random variable, so we're going to have functions of 2 variables. So the kind of reading video is going to be an introduction to that. We haven't talked about exponential distribution yet, so I'll start with that. You guys don't need to read ahead about this if you don't want to, and then we'll move on to the next worksheet. So you should be able to get through most of the homework that's due next week if you want to get started really early. There are some questions that have an exponential distribution on it, so that's probably the one question you might not be able to get to just yet. So if that looks weird, don't worry about it. We'll start class on Wednesday with that. Okay, well, thanks everybody. If you have any questions, you and I are around for office hours today or tomorrow, and homework is due by midnight tonight. And otherwise, I'll see everybody on Wednesday. Thanks.
Thank you.
Thank you.